Hello, everyone. In this lecture, we're going to discuss non-autonomous ODE system solver and the stability analysis. My name is YingWang. I'm a mathematics professor from University of Oklahoma. We're going to focus on this carbon dynamics model. X prime is equal to C times A times C times X plus B times U. By now, I believe you have seen this model multiple times. Here, X is a vector of carbon pool sizes, and C is an environmental scalar. A and C are carbon transfer coefficients between plant, litter, and soil pools. They are usually matrices. U is the photosynthesis parameter, and B is the vector partitioning coefficients. We're going to study two aspects of this carbon dynamics model. One is we're going to derive the analytical solution for this carbon dynamics model. And the second part, we're going to study the stability analysis. Before I give any details of this, I want to emphasize that this model is a non-autonomous model and also non-homogeneous. Non-autonomous means the right-hand side of the equation depends on the independent variable t explicitly. For example, the C here and the U here, they both depend on t explicitly, so it's non-autonomous. Non-homogeneous means that there's a term in this differential equation that does not involve x. For example, b times u here does not involve x. So it's a non-autonomous, non-homogeneous model. In order to derive the analytical solution for this model is non-trivial. So we're going to do this step by step. We're first going to study the solution for a scalar equation. And then we're going to apply this to one pool model instead of an n pool model. Here in general, we would assume that we have n pools. And then we're going to move on to system cases. There are two cases for system. One is homogeneous, one is non-homogeneous. And then afterwards, we're going to apply the solution, general solution to the n pool model. That's our ultimate goal, to solve for the n pool model. And for the stability analysis, so we're going to study three cases. First case is x prime is equal to A times x, which is a homogeneous system with a constant coefficient matrix A. Second case is x prime is equal to A times x plus B times x. Here B is a function explicitly dependent on t. So this is a non-autonomous system, but it's a homogeneous. Third case, we're going to study the most general case, which is non-autonomous and non-homogeneous. The F term here makes this equation non-homogeneous, and the B and F together, they make this equation non-autonomous. We're going to walk through those two topics one by one. We're now going to start with the analytical solution for a scalar equation. The scalar equation we're going to study is in the following form. X prime is equal to P times X is equal to Q. This is a first order linear equation. First order in the sense that we only see first order derivative. Linear in the sense that we do not see x prime as x squared term, x cubed term, or sine x, any nonlinear x term. So therefore, it's a first order linear equation. A standard way to solve the first order linear equation is to use integrating factor method. We first construct the integrating factor, which is e to the power of a capital P. Capital P is the integral of the small p. And then we're going to multiply the integrating factor across the entire equation. This is what we get. And then we realize that the left-hand side of the equation by product rule is nothing but the derivative of the product of these two functions. First function is the integrating factor. Second function is our original unknown x. In order to solve for this equation, we're going to integrate this entire equation. On the left-hand side, we do not see the derivative anymore after integration. The right-hand side is the integral of the original right-hand side here. To recover our unknown x, we will divide the entire equation by the coefficient e to the power of a capital P. So this will be the solution formula for the first order linear equation in this standard form. Now I'm going to give you a concrete example. This example is x prime minus x is equal to e to the power of 2t. First, we construct the integrating factor, e to the power of capital P, which is the integral of -1. That's e to the power of -t plus t naught. And then we're going to multiply this integrating factor across the entire equation. Then the left-hand side of the equation becomes the derivative of the product of two functions. First function is integrating factor. Second function is x, our original unknown. The right-hand side is integrating factor e to the power of negative t times the original right-hand side. Notice that e to the power of t naught here, this is common to both left-hand side and right-hand side. Therefore, this term can be canceled. And then afterwards, we're going to integrate this equation. Left-hand side becomes e to the power of negative t times x. Right-hand side after integral is still itself with the integration constant here. So to recover x, we're going to divide the entire equation or multiply the entire equation by e to the power of positive t. So x is equal to e to the power of 2t plus c times e to the power of t. Plug in the initial condition at t is equal to 0. We get that the integration constant c is the initial condition minus 1. Okay, now we're going to consider one pool model, which is our carbon dynamics model, assuming that there's only one pool. What that means is all the quantity we see here are scalars, meaning A, C, those are not matrices anymore, they are scalars, and B is not a vector anymore, it's also scalar. Notice that this equation is exactly the first order linear equation we just discussed. Here, the P, that's coefficient in front of X, that will be, in this case, equal to negative C times A times C. And the Q, in this case, will be equal to B times U here. Then we can apply the solution formula we derived earlier to solve this equation. So the solution for this one pool model, that will be equal to e to the power of negative capital P times the integral of e to the power of positive capital P times Q, Q is BU, plus integration constant. I can pull back the slide to remind you the solution formula. Here's the solution formula, e to the power of negative capital P times integral of e to the power of positive capital P times Q, plus integration constant. And here, the capital P is integral of the small p. That's the integral of negative c times A times C. The integration constant C here, sorry, there's abuse of notation. This C is the integration constant, which is different from this transition matrix coefficient here. So integration constant C, plug in the initial condition at T naught, it will be able to figure out that C is nothing but X T naught. Now we are going to move on to the system case because by the end, we want to solve for n pool model, not just one pool. So that will be a system. So to study the system case, we first studied the homogeneous system, x prime is equal to A times X. We supply the system with a set of initial conditions, E1, E2 up to En. We assume we have an n pool, meaning X is a vector of n dimension. E1 is a n-dimensional vector with the first component equals to 1, everything else equal to 0. E2 is only the second component is equal to 1, everything else is equal to 0, and so on. So all those EIs, they are, each one of them is a standard basis in the Rn space. For each of the initial condition EI combined together with the differential equation x prime is equal to A times X, the homogeneous system, we will be able to get a unique solution for this initial value problem. For E1, the corresponding solution, we call it X1. For E2, the corresponding solution, we call it X2, and so on. So we'll get the n solutions corresponding to E1, E2 up to En. And we're going to put all the n solutions as vectors, put them together to form a matrix. This matrix is a so-called fundamental matrix of this homogeneous system. X prime is equal to A times X. Notice that each of those xi is a solution to this equation, meaning x1 prime is equal to A times x1, x2 prime is equal to A times x2, and so on. Xn prime is equal to A times xn. So what that means is the fundamental matrix phi also satisfies this equation. Phi prime is also equal to A times phi. This is an important point we're going to need to use in the next slide. So I want to I want to actually draw your attention here. Next slide, we're going to move on to non-homogeneous equation. So non-homogeneous equation meaning we have a non-homogeneous term which is independent of x. The solution of the non-homogeneous system has a following form: phi times q. Phi is the fundamental matrix for the associated homogeneous equation x prime is equal to a times x. Q is a vector, q1, q2 up to qn. So the solution is a matrix times a vector. By the definition of matrix vector multiplication, this will be linear combination of all the columns here, and the coefficient for the linear combination, that's q1 up to qn. And each column in phi, that's x1, x2 up to xn. So this capital X solution will be q1 times x1 plus q2 times x2 plus all the way qn times xn. So linear combination of linearly independent solutions for the corresponding homogeneous system. Okay, and here our main goal actually is to find out what this Q is, because we know the fundamental solution for the homogeneous system already. Once we know the Q, then we are all set. We will be able to write down the solution explicitly. In order to find out the Q, we will plug the solution into the equation. Because it's a solution, it should satisfy this equation. And left-hand side here, x prime, by product rule, this will generate us these two terms. And A is A here, and X, that is phi times Q, okay? G is G here. And now, remember we said that since phi is a fundamental matrix, therefore phi satisfies the homogeneous equation. X prime is equal to A times X, meaning phi prime is equal to A times phi. Therefore, this term is equal to this term. So the first term on the left-hand side can cancel with the first term on the right-hand side. Therefore, the second term on the left-hand side is equal to the second term on the right-hand side. That's our starting point here. And then Q, in order to find out what the Q is equal to, we first solve for a Q prime. And Q prime, that will be equal to, we multiply the inverse of a matrix phi throughout the entire equation so that phi disappears from the left. And this step is valid because phi is a fundamental matrix, therefore it's obviously invertible. Each of the column here is an independent solution for the corresponding homogeneous system, therefore it's invertible. And then in order to solve for Q, we'll integrate the right-hand side here, that's the Q. Now we have the solution for Q, we can easily write down our solution for the non-homogeneous system, which is a phi times Q. Phi is the fundamental matrix for the associated homogeneous system, and Q is here. Therefore, solution X is equal to phi times C plus phi times this integral here. And then we plug in the initial condition at the T naught, we'll be able to find out the integration constant C here. Now, we're going to move on to our N-pool model. That's our ultimate goal to solve. X prime is equal to C times A times C times X plus B times U. We give initial condition X naught. This actually is exactly a non-homogeneous ODE system we have just discussed. In this case, so let me pull back the non-homogeneous ODE. So that's like this: X prime is equal to A times X plus G. And so for our N-pool model, A is nothing but C times A times C. And the G is this non-homogeneous part, this B U times T. So we can apply our solution formula to write down the solution for this N-pool model. The solution formula that's in the previous slide, that's phi times C plus phi times this integral. So phi, in this case, this is the fundamental solution, fundamental matrix for the corresponding homogeneous system here, and which is exactly this thing. C is just X naught, okay? And here inside this integral, you have phi inverse at S. So that means is here, this will be integral from negative S to 0. And then you move this to into this integral, you have the phi here combined together with the phi inverse, that will be integral from S to T. Okay, so that's why this part is phi times phi inverse, and the g is b times u. And since b is independent of the integration constant, integration variable s, therefore b is pulled out of the integral, and u is dependent to the integration variable s, so it's staying inside the integral. What we need to do is to figure out what is the fundamental matrix phi, meaning this highlighted part. So this is a matrix exponential function, but the exponent is a matrix. A times c is a matrix, and this integral is a scalar. Let me remind you what is exponential function. For scalar case, exponential function is defined as this infinite series. For matrix exponential, it's also defined in the same way. However, this definition is not very useful in the sense that it's not constructive. So for special cases, we do have a constructive way to calculate the matrix integral. For example, if the matrix A is a diagonal matrix, meaning only the diagonal entrants are non-zero, all the other entrants are zero, then e to the power of A is also a diagonal matrix with the diagonals being exponentiated. Another special case is even if A is not a diagonal matrix, if A is diagonalizable, what that means is you can find an invertible matrix P, which usually is the eigenvector matrix of matrix A. And A can be written as P times lambda. Lambda is the eigenvalue matrix, which is diagonal matrix with eigenvalues of A sitting on the diagonals, times P inverse. If A can be diagonalized like this, then e to the power of A is equal to P times e to the power of this diagonal matrix, e to the power of lambda times P inverse. And for diagonal matrix, we know how to calculate its exponential. We saw this in the previous case here. Okay, now our goal is to find out how to calculate the matrix exponential or the fundamental matrix phi here. In order to do that, we first introduce an auxiliary variable, small phi. You see the difference between the small phi and the capital phi is instead of this complicated function, small phi just use a t here. So AC, the matrix part is the same, is only the scalar part is a lot simpler. Okay, and here for the matrix AC, we assume that the eigenvalues, so it has an eigenvalues, the counting multiplicity, lambda 1 up to lambda m. And it also has n linearly independent eigenvectors. We actually need autonomal eigenvectors so that we can diagonalize matrix A. Okay, and then we use those autonomal eigenvectors to form the eigenvector matrix capital V, so that the matrix AC can be diagonalized in the following way. It's equal to V times the eigenvalue matrix, its own eigenvalue matrix, meaning it's a diagonal matrix with all the eigenvalues, lambda 1, lambda 2, all the way to lambda n sitting on the diagonals, on the diagonal, times the V inverse. V is the eigenvector matrix. And then AC matrix times scalar C times scalar T is nothing but you multiply T to every diagonal entrant there. Okay. Then in that case, the small phi here, okay, the small phi, which is e to the power of AC times T, since the AC times T, this is diagonalizable, therefore it's just equal to, you diagonalize every single diagonal entrant here. You exponentiate every single diagonal entrant here, and the V stays here, V inverse stays there. Okay, once we have a small phi, we can calculate our capital phi. Remember, our capital phi is nothing but small phi. Instead of t here, we have this more complicated function. Now we call this f. So the capital phi is just v times, whenever we see a small t here, that will be f here, okay? And here, just spell the f out. Now we have the fundamental matrix phi for the associated homogeneous system. Then we can write down the solution. So the solution formula here, that's the solution formula for our N-pool model. It has two parts. The term A and term D. Term A is 5 times C, term D is 5 times this integral here, meaning this is this integral here. So for A, term A is simple, it's just 5 times C is x naught. And for term D here, we have this integral times matrix B, which is a constant. And this integral, inside this integral, we have exponential function here. This matrix exponential we have already explained. This is just a V times a diagonal matrix. All the diagonal entrants are e to the power of the eigenvalue of AC times whatever follows it. So this is originally for small phi, this is t. Now for capital phi is this integral here, small f here. And the V inverse stays here, and the U is here. And now V and a V inverse, they are constant matrices, so they are independent of the integration variable s. So those two can be pulled out of the integral sign here. And then here is integral of a diagonal matrix. It's the same as you integrate every single diagonal entrant here. Then this way you again have a diagonal matrix. You just write out the diagonal matrix explicitly. By doing this, we are finished with the analytical solution for N-pool model. So now we're going to move on to the second topic, the stability analysis. We're going to do this for 3 cases. First case is for a homogeneous system with a constant coefficient matrix A. Suppose A has n eigenvalues counting multiplicity, and x hat is x tilde is equilibrium point. If all eigenvalues has real part negative, then the equilibrium point is asymptotically stable. If all the eigenvalues has real part non-positive, and those with real part equal to 0, they're all simple, then x tilde is a stable equilibrium point. If there are eigenvalues with 0 real part but it's not simple, then the equilibrium point x tilde is unstable. If you can find any eigenvalue with positive real part, then the equilibrium point is unstable. The second case is a little bit more general than the first case. We do allow to have a non-autonomous term, meaning we allow another coefficient for x, which is t-dependent. We assume this coefficient is a continuous function of t. Again, lambdas are eigenvalues for matrix A. Counting multiplicity, there are n eigenvalues, and x tilde is the equilibrium point. If all the eigenvalues has real part negative, and also the limit of the B function is equal to 0, then the equilibrium point is asymptotically stable. If all the eigenvalues has real part non-positive, and those with 0 real part, they are simple, and also integral of the speed function is bounded, then the equilibrium point is stable. If there is an eigenvalue with positive real part, even if the limit of B is equal to 0, the equilibrium point is still unstable. The third case is the most general case, which is non-autonomous and non-homogeneous. So this will make it non-autonomous. F will also make it non-autonomous because it's t-dependent. And F also makes the whole equation non-homogeneous because it's not x. We assume that B is a continuous function and x naught is equilibrium point. If the limit of B is equal to 0 and this function f is continuous in t and it has a continuous partial derivative in x, and also the limit of this fraction f divided by x is equal to 0 uniformly in P, then if all the eigenvalues has real part strictly less than 0, then the equilibrium point is asymptotically stable. If there is an eigenvalue with a positive real part, then the equilibrium point is unstable. All the other cases, the stability is not clear. So far we have discussed the stability for 3 general cases. In the lecture notes, you will also be able to see the discussion on instantaneous equilibrium point, and also global attractor, and also derivation of global attractor for N-pool model, and also its relationship with instantaneous steady state. Lecture notes also provide you examples for solution for a three-pool model, for analytical solution for three-pool model. So you'll be able to find a lot more details in the lecture notes. Thank you all for coming to this lecture.